Okay, so now we're going to talk about Giancoli 8.5 and inertia when we talk about in rotation. So torque and rotational inertia. So really quick, knowing that force equals mass times acceleration, we know that torque equals mass times radius squared times angular acceleration. So now this is for a single point mass. What about an extended object? And as the angular acceleration is the same for the whole object, we can write this. So net force is, or sum of force, or sum of the torque is equal to the sum of mass times radius squared, right? So the sum of all the masses, or the inertia, times the angular acceleration. And this is how we find that information. All right. So just keep that in mind as we talk about things and go through problems. So the quantity inertia is equal to this, right? The sum of mr squared. It's called rotational inertia of an object. It's the distribution of mass does matter, all right? These two objects here have the same mass, but one on the left has a greater rotational inertia as so much of its mass is so far away from the axis of rotation, okay? So as the mass gets farther away from the axis of rotation, the greater the inertia is. All right. And remember inertia, the difficulty to stop something from moving or to start something moving. So it's easier to get this to start and stop than it is this once they start spinning, is what we're saying here. Okay. So now rotational inertia of different objects. And this diagram is a lot to look at. Okay. But the big thing is that when we talk about moment of inertia, these equations can be used. Do you have to memorize them? The answer is no. Okay. Should you know how to use them if you see a problem? And the answer is yes. All right. So we'll look at some of these with the homework, and then also just trying to understand what that information is going to be important, especially if you move on and you're going to be an engineer. These are things that you'll probably use a lot more than we will today. Okay, as we talk about them. So you can see the different objects, their shapes, location of the axis, and then more importantly, how to find the moment of inertia. Okay, and it says compare F and G. So here we have two rods, one with the axis in the center, and one at the end, and you can see the difference just in the moment of inertia is there. Okay, so let's talk about this problem that's similar to what we just saw. Two weights on a bar, different axis, different I. So two small weights of mass 5 and 7 are mounted 4 meters apart on a light rod whose mass we're going to ignore, as shown in this diagram. We're going to calculate the moment of inertia of the system when A, it's rotated in the midway point, and B, when it's rotated almost at the end. Okay? Do it now.
All right, so find the moment of inertia. Two situations. We have this bar swinging this way, right? Um, and we're doing it from the center. Here we're swinging around this way with the longer end here, and we have some measurements. But we want to find the moment of inertia based on the weights. So essentially the moment of inertia is the sum of the mass times the radius or distance squared. So we got here and here, since it's smack dab in the middle, this distance will be 2 meters from the center, and this will be 2 meters from the center. So I just take 5 times 2 squared plus 7 times 2 squared. And that should tell me my moment of inertia, or my area inertia. So 5 times 4 is 20, plus 7 times 4, 28. So 48. And your units are kilograms times meters squared. So the I is going to be that. The moment of inertia will be at 48. So now we have this same instance. We have a different instance where we're spinning here. Now the 5 is half a meter away, while the 7 is going to be 4.5 meters away. So we want to find the moment of inertia there, and exactly it's the same. Sum of mass times the radius squared, or the distance squared, right? So I start here, the mass of 5 times the distance of 0.5 squared plus the mass of 7 times 4.5 squared. This one's going to be a little more difficult to do. 5 times 0.5 squared should be 1 1/4. Yep, I guess I can do that one. This one is 7 times 4.5 squared, 141.75. So 142, 143. So this has a much higher moment of inertia. And really, this gives us a couple of different things to think about. First, the moment of inertia is different for a different axis of rotation. And second, if you look at close B, or look at part B, this mass being here has an effect, okay? It contributes little to the moment of inertia, but this is where most of the moment of inertia comes from. So the closer we are, the less we contain the moment of inertia, or how it controls or affects the moment of inertia.